Alright, let's try this one here. This one could be a little bit tricky. Let's see. Alright, let's start off. A. The pitcher accelerates a ball to the right, so that's a positive acceleration, increasing its velocity from 0 to 40 in 0.5 seconds. So that'd be like this. Now, it's going to travel to the right at 40 meters per second, which is where I am now. Keep in mind, this axis is how fast you're going. And it's going to travel that way for 0.7 seconds. So we're going to go 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. Alright, and then what's going to happen is the batter hits the ball to the left, which is our negative direction, changing its velocity in 0.5 seconds to 50 meters per second to the left. That's negative 50 on this. Since we've decided we've made going to the right is positive and going to the left is negative, so it's going to end up at negative 50 in 0.5 seconds, which means it's going to end up at negative 50 in 0.5 seconds, which is this. So that should be right. Let's see if we got it right. 1, 2, 3, 4, 5. Yep. Okay. So now it's going negative 50. And now the ball is going to travel to the left, reaching the pitcher in 0.6 seconds. So we're going to go 0.1, 2, 3, 4, 5, 6. And then the pitcher catches the ball. Oh, it's an out. Bring it to a stop in 0.3 seconds. That means its velocity is going to reach 0 in 0.3 seconds. And that means we're going to go like this. So there is our motion velocity versus time graph for that scenario. Now what we're going to do is we're going to take it and we're going to turn it into an acceleration time graph, which means I've got to calculate the acceleration. Now one thing to keep in mind is when the baseball is traveling to the right or the left, the acceleration at those times equals 0. So I have 0 meters per second squared. The ball travels to the left, reaching that's 0 meters per second squared. Okay, so it's accelerating at 3 different times on the graph. Anytime it's not accelerating here and it's not accelerating here, but it's accelerating here and here and here. When it's thrown, when it's hit by the bat, and when it's caught by the pitch. Now, granted, this is not very realistic. I don't think it'd take half a second to hit the baseball, but I wanted you to be able to see the slope. So let's just try this here. First, let's calculate this. So on A, when the pitcher does it, what it does is it goes from 0 to 40. So it changes 40, and it does it in 0.5 seconds. So I'm just going to say 40 meters per second divided by 0.5, and that gives me a, correct me if I'm wrong, but I believe that gives me an 80 meters per second acceleration initially. So let's go down to our graph and put 80 on there. Oops, so we're going to go down here. So for the first 0.5 seconds, it was accelerating at 80 meters per second. So I'm going to go up to 80. We're getting 50, so I'm going to say this is about 80 for 0.1, 2, 3, 4. Okay. And then it's, if you look at the next segment, it's traveling at constant velocity. That means it has an acceleration of 0. So acceleration versus time graphs look kind of funky. They look kind of sawtooth. They're just going to drop down, and it's going to go, how many seconds did I say that was? Let me look again. It's traveling for I believe I changed this from 0.8 on your paper to 0.7. Alright, so let's just try this here then. And while I'm at it, I just got to remember this one was changed to 0.5. 0.5. Okay, so sorry for the mess here. Alright, so let's go down here then. What I'm going to do is it travels this way for 0.7 seconds at 0. 1, 2, 3, 4, 5, 6, 7. Does that look right? Yeah, 0.7. And then what happens is it gets whacked by the pitcher, or not by the pitcher, by the batter. And look what it does. it goes from being positive 40 to negative 50, and it does that in 0.5 seconds. So that's a total change from positive. So remember, the way you find the change is you take the ending one, which is negative 50, minus the initial, which is 40. That gives me a total delta V of negative 90 meters per second divided by 0.5 seconds. That's negative 180 meters per second. So I had to come down to negative 180, and a little more, I guess. And it's going to stay for 0.5 seconds. 1, 2, 3, 4, 5. I hope I did that right. Okay. And then what happens is it's going to travel to the left for another 0.6 seconds. Well, for that 0.6 seconds, it's not accelerating. 1, 2, 3, 4, 5, 6. So that right there represents the time it was traveling at a constant negative 50 meters per second to the left. Now it's going to get caught by the pitcher. So the pitcher is going to cause the pitcher catches it, and remember, it's going to slow down in the negative direction. So if it slows down in the negative direction, it's going to go up to here. Now if you look, the positives, I went from negative 50 to 0. So it's basically speeding up from negative 50 to 0. That's a positive slope. Just like that's a positive slope. So a positive slope means a positive acceleration, and a negative slope means a negative acceleration, and a slope of 0 means 0 acceleration. And if you forget, just remember, on a velocity versus time graph, the slope is meters per second divided by second. Meters per second, meters per second squared. So the point is, I have a positive acceleration of, it's going to go from negative 50 to 0. So that's a change of 50 in 0.3 seconds. So if I say 50 in 0.3 seconds, that's going to equal basically 166. So now it's a positive acceleration. So I had to go. So we're going to go up to 166, which is, oops, wrong thing here. 166 for 3 seconds. Oh yeah, looks a little bit different, doesn't it? Alright, but you can see what we've got here is, if you look at the two, when I have a positive acceleration, I have a positive acceleration. When the acceleration goes to 0, it's flat. When it has a negative acceleration, I have a negative acceleration. For the amount of time that it's traveling horizontally without accelerating, I have an acceleration of 0. And when I catch it, I produce a positive acceleration right here. Okay, well, let's try the next one. And you're seeing these things are a little tricky here, huh? Alright, a rubber ball is dropped out of a high-rise building. Alright, it falls for 6 seconds, immediately bounces up to half the speed it hit with and falls back to the ground, lands in a mud puddle and stops. Draw this graph below, and good luck. Now, bouncing balls have an interesting look to them. So remember, I release it from rest, so its initial velocity is 0. And it's going to accelerate at negative 10 meters per second for 6 seconds, which means after 6 seconds it will have gone to a velocity of negative 60. So it's going to end up right here. So it's going to go from, it's basically going to go, I'm going to draw it in the reverse order because it's easier to see. Alright, so basically what happens is when I let go of it, it accelerates at 10 meters per second, negative 10 meters per second for 6 seconds, reaching a speed of negative 60. Now, it hit the ground. Now look what happens. After it hits the ground, it immediately bounces up at half the speed it hit with. Now, which way is it moving at this point? When it bounces, here it was falling down. Now, it's going to be moving upwards. Right, but remember, up on this graph does not mean up in the real world. I now have an upward velocity. Upward is the positive direction. Now it has a positive velocity that's half as large as its negative velocity. So its negative velocity was negative 60. So now it's immediately going to have a positive 30 meter per second velocity. It's going in the positive direction. So that's what happens when balls bounce. You get this weird little sawtooth thing. Now it's falling again, and as it falls, it's going to accelerate at 10 meters per second. Now it's weird on the graph like this. As it moves up, it slows down at negative 10 meters per second. It's slowing down in the positive direction. So that means it's going to take it 3 seconds to get to where it is now at a velocity of 0. So it's going to go like this. Okay, so it's falling down for 3 seconds at 10 meters per second. At this point right here, this is where it stopped moving upwards. It started moving upwards here, it slowed down, and now it's reached 0. Now its velocity is going to become negative as it falls back to the ground. So it basically is going to fall down. If you throw something up at 30, it's going to go up for 3 seconds, so it's going to fall down for 3 seconds. So I'm going to continue at this slope for another 3 seconds, which means I'm going to reach negative 30, and I'll do that in another 3 seconds. So let's find where negative 30 is. Let's see if I can draw it right. 1, 2, 3. Am I at negative 30? I think I'm at negative 30, yes. I'm at the 12-second mark, great. Now what happened to it now? It hit a puddle and it stopped, so its velocity is going to go to 0. That's what it should look like. Did you get it? That's a kind of tricky one, isn't it? Alright, let's keep going. Okay, now this is an actual AP question here. That's why it looks different. I took it out of the only release test that they've given so far, and the way they had it was that these graphs here were put above it, so I had to cross that out. But here's what we've got. We've got a position versus time graph where we see the position goes negative and comes back up to where this is where we started. It moves away from us and it comes back. We look here on the velocity versus time. It had a negative velocity and it had less and less and less negative velocity. It stopped and then it developed a positive velocity. And the whole time, therefore, it had a positive slope, so it had a positive acceleration. What's tricky on this one is it says which could describe the motion. Now, we often use gravitation as being negative. We say, well, it's moving in the downward direction. Well, we're on a ramp. We get to choose what we want to call the positive and negative direction. So let's just see which one of these we can rule out. All right, let's look at this first one. It says rolling along the floor and then bouncing off a wall. Well, if it rolled along the floor and bounced off a wall, what would happen is we wouldn't get this constant rate of acceleration. During that time of a bounce, we get a very different acceleration. So anytime it says bouncing, we just looked at what bouncing, this is what bouncing looks like. That's definitely not the kind of graph we're getting here. If you look at this velocity time graph, I don't see a bounce there. I see a continuous slope. How about rolling down one side of a bowl and back up the other? Well, if it rolled down one side of a bowl and back up the other, where would it have reached its maximum velocity? Its maximum speed would have been at the bottom of the bowl. So halfway through the trip, instead of having a velocity equal to 0, which is what this line represents, we'd be at our maximum. So that one doesn't make sense. So what that leaves us with is this one here, rolling up a ramp and then back down. So it left our hands here, and we're defining that as a negative velocity. It slows down as it goes up the ramp, reaches 0. So when I say slows down, it loses its negative velocity, reaches 0, and then it develops a positive velocity. It moved away from us, and then it came back to us, and the whole time it accelerated at a constant rate. So the answer is rolling up a ramp and then back down. Let's continue. This one is diabolical. Alright, we got an astronaut on a cliff on an alien planet. Let's see. Released at time 0. So at this point right here, the astronaut lets go of it. Now, the astronaut apparently threw it. Okay. We're going to use downward as a negative direction. Alright. So what is the acceleration of gravity on this planet? Well, we notice is the rate at which this changes. Now, I'm just going to do it this simple way. I'm going to measure it from here to here. So what I see here is this is 40 and this is 0, and the amount of time is 8 seconds. So I'm going to say the final velocity minus the minus the initial velocity, which is 40, divided by the time, which is 8 seconds. So what that's going to give me, 40 divided by 8, is negative 5 meters per second squared. So here you go. The acceleration on this planet is negative 5 meters per second squared. In other words, every second that goes by, this is going 5 meters per second slower. And it's going to continue to do that for a ways. Now, was the ball thrown upwards or downwards? Well, it left our hands with a positive velocity of 40, meaning it was thrown upwards, because we're defining upward as a positive direction, and since it left my hand at positive 40, it must have been thrown upwards. When did the ball reach its highest point? Now, you might say, well, it's either here or it's here, but actually it reached its highest point right here. Because think about it, I threw it upwards. Although this is moving downwards on our graph, the velocity is what's changing. So it left my hand, it was going up at 50, now it's going up at 40, now it's going up at 30, it's going up at 20, it's going up at 10, and now it finally stopped moving upwards. So here is where it's at its highest point. At time 8 is when it's at its highest point. Then the velocity becomes negative. So when did it pass the astronaut? Well, here's the thing, gravity is very symmetrical. So if I throw it up at 40, when it comes back to me, it's going to be going 40, but instead of 40 in a positive direction, it should be going 40 in a negative direction. So I'm just going to follow this down until I get to 40 in the negative direction, which is right about here, I would say. It looks to me like that's at the 16-second mark. At 16 seconds, it passes by the astronaut and keeps falling downwards because he's on a cliff. At what time did the ball reach the ground? Well, it reaches the ground here, where it changes from having a negative velocity to suddenly having a positive velocity as it bounces upwards. So it touched the ground at time 20. And what was the ball doing at the 26-second mark? Now, so think about this. The ball hit the ground, and it immediately developed a positive 30 meter per second velocity. So positive means upwards. So now what happens is it starts accelerating in a negative fashion. So right now it's moving up at positive 30, it's moving upwards at positive 20, it's moving up at positive 10. Hey, it just stopped moving upwards. So this doesn't mean it's at the ground, this means it stopped moving upwards. So what it did is it is at the top of its bounce. Okay, it's at top of bounce. Or we could say it's at its apex. Cool. Let's try another one. Ooh, draw a velocity versus time graph which depicts the following events. Oh, this looks killer. A bowling ball initially at rest is thrown upward, reaching a velocity of 6 in 0.4. Grr. Alright, let's just try this here. I'm going to make this a little bit smaller. Okay. So, alright, on my velocity versus time graph, it's going to reach a velocity of 6, and it's going to do that in 0.4 seconds. Did I change these numbers at all? Oh, thank goodness I did, in 0.4 seconds. So, I'm just going to go, let's say, it's going to, let's see, I'm going to have to go like this. So it's going to go to 6, which is here, in 0.1, 2, 3, 4. So what I'm going to do is I'm going to go here, and I'm going to go, that's what it just did. So it went like this. In 0.4 seconds, it went from 0 to 6. Now, after being thrown in the air for after being in the air for 1.2 seconds, the bowling ball lands on the trampoline. Now the whole 1.2 seconds, we're assuming we're on Earth, it's accelerating at 10 meters per second per second. So if it's accelerating at 10 meters per second, how long is it going to take it to go from 6 meters per second to 0 meters per second? The answer is it's going to take it 0.6 seconds. So let's go another 0.6. 0.1, 2, 3, 4, 5, 6. So it will reach its apex here. Okay. Let's see. Alright, so I need to, at this point here, I need to draw a line. I hope I did it right. Now it's at the apex. It's just reached a velocity of 0. Well, guess what? Now it's going to fall down, huh? And it's going to fall down for 1.2 seconds. So here it goes for another 1.2 seconds. It's going to go, I'm sorry, for another 0.6 seconds, it's going to pick up another 6 meters per second in the negative direction. So what I have to do is I have to get down to negative 6, which is here. And I have to get there in 0.6 seconds, so I'm going to go, I've got to be careful here, because I screwed up once already. Okay, so that's 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. So let me just try to draw this in now. There you go. So, alright, now what's going to happen? The next thing that happens is the trampoline brings it to a rest and sends it upwards at 4 meters per second in 0.6. So I've got to get from here, from negative 6, and I have to get up to positive 4, and I have to do it in 0.6 seconds. So I'm going to go 1, 2, 3, 4, 5, 6, and I'm going to go up to 1, 2, 3, 4. So I got to get a line that connects these. Oops, wrong thing. Alright, and then what happens? The ball lands on the ground 1 second after leaving the trampoline. So I have to go over 1 second, and it's going to land on the ground and come to a stop. So that means if it falls for 1 second, it's going to change its velocity 10 meters per second. 10 meters per second, so you fall for 1 second, you change it 10. So that means right now it's at 4. It needs to lose another 6. So I had to come back down here to 6. Now notice something. The slope here and the slope here are the same, because this is negative 10 meters per second and this is negative 10 meters per second. And now we're going to bring it to a rest. There you go. Last thing we got to do on this homework assignment is turn this graph here into an acceleration versus time graph. Well, what we have here is an acceleration of, let's see, it's 6 meters per second in 0.4 seconds. So that means what we've got is, we've got 6 divided by 0.4. Let's see what that is. 6 divided by 0.4. That's 15 meters per second, and that is a positive acceleration of 15. I guess I should write 15 here. That equals 15. Alright, so I'm going to come up to 15, which I think is about here, and I'm going to go there for 0.1, and I'm going to do 2 high, 2, 3, 4. Okay. Then what happens? Well, then it would, for the next, how long was it? 1.2 seconds? For the next 1.2 seconds, it had a negative 10 meter per second acceleration. So I'm going to drop this sucker down from here down to negative 10, and it's going to stay there for 1.2 seconds. And I'll probably screw up my counting, but wish me luck with this. Okay. 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I think I got lost. I don't know if I got it right or not. If I got it wrong, I apologize. Now what's going to happen? Well, now what's going to happen here is, to calculate the acceleration here, we have to see what the change in velocity is. So at this point here, we're going negative 6. Here we're at positive 4. That's a change of 10. That's 10 meters per second change in velocity. Just put that here. We changed 10 meters per second, and we did it in 0.6. So 10 divided by 0.6, that's 16, let's just call it 17 meters per second. So now what I have to do is I have to come up to 17 meters per second. What was I at before? I was at 15, so I gotta come up to 17. Alright, so here we go. We're going up to 17. So we're going up to 17. Oops. We're going up to 17 straight up to here. And it's going to stay there for how much time was it? Let's see, 0.6 seconds. So 0.1, 1, 2, 3, 4, 5, 6. And then it's going to fall down for 1 second. So it's going to have a negative 10 meter per second acceleration for the next second. So I'm going to come down to negative 10. And it's going to stay there until it gets to here. And now it's going to hit the ground. And when it hits the ground, it's going to have a rather large acceleration. It's going to go from this velocity here, which is like negative 6 to 0 in a very short amount of time. So it's a very large acceleration, but then that's where we leave it off. Hey, tricky, takes a little bit of work. You definitely have to think to get these right. If you didn't get it right, don't worry, I'll help you with it, and we'll get you to where you can do these with confidence.